Hey guys, so today we're going to be talking about bond energy and bond length. Let's start off with a little bit of bond energy things. So all of you know that two ropes tying two things together is obviously much stronger than having one rope tied two things together. This is exactly the same for atoms. A double bond between two atoms is usually twice as strong as two atoms connected by a single bond. But here's the thing, because the atoms are vibrating, the bonds are vibrating as well. However, these vibrations are also very closely related to bond energy, also referred to as bond strength. Bond energy formula is E equals H times V. E is obviously bond energy, where E is for, energy. The H is a fundamental thing in physics and chemistry called the Planck's constant. Planck's constant is 6.626070015 times 10 to the negative 34th power joule second. For clarification though, this isn't joules per second, it's joule times second. This is because sometimes you might get confused and this will get your bond energy unit wrong. Frequency is measured in x times per second, which is often referred to as the hertz. When we multiply the two of them together, because the second is in the numerator and this second is in the denominator, these 2 seconds will cancel each other out, and eventually we're going to get a quantity in the unit of joules. Joules is the unit for energy, and this confirms that our formula is correct. A way to measure bond energy is by heat of combustion. For instance, I have 3 very closely related organic compounds, ethane, ethene, and ethine. All of these compounds are organic and highly flammable, and when you burn them, you get these amounts of energy from them. As you can see, ethane has the highest heat of combustion, while ethine has the lowest. The reason is because of this carbon-carbon single bond. This carbon-carbon single bond obviously has the weakest bond, and because of that, it's very easy to snap the two of them apart. Because of this, we don't have to waste too much energy into breaking that bond. As you get to ethene though, it starts to get a double bond, which is much stronger, and it will consume more energy to break those two atoms apart. And when we get to ethine, we have a triple bond, which is extremely powerful and is very hard to break, so we're going to waste a lot of energy trying to break that bond while combusting. Now let's get into bond length. We have 2 major ways to measure bond length. The first one is to use something called X-ray crystallography. All we have to do is get a crystal of the substance and then shoot X-rays through it. The idea is that we measure the diffraction of X-rays because of a single crystal, and then we measure the bond length. Another way is infrared spectroscopy. This is because the vibrations of the molecules are measured in the infrared spectrum. So if we use the infrared spectrum to observe these molecules, we can observe the bond length. Here's a quick chart for the bond length and energy for common covalent bonds. This is a carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond, nitrogen-nitrogen single bond, double bond, triple bond, and finally we have carbon-oxygen single and double bonds. As you can see, we have a slight trend here. As the bonds get stronger and stronger from single to double to triple, the bond energy increases, and the bond length of course goes down. This is because the stronger the bonds, the shorter the bonds get, so it's logical that the lengths will decrease. Also, just as a side note, this is a unit called picometers. Picometers is 1 trillionth of a meter, or 1/1000th of a nanometer, which is, incredibly tiny. So once you're done memorizing, let's go to nomenclature for just a second before we end the video. You see, covalent compounds all have a way of systematically naming them. But the thing is, a lot of them were discovered way before our modern way of naming was invented, so they all have something called a trivial name. This is their old day names that people used before our modern naming system was invented, like water, methane, nitrous, or ammonia. In the modern days, though, we have something called a systematic name for each and every chemical compound, including covalent compounds. So here I have a chart for very common and very important chemical compounds and their trivial and systematic names. The ones I highlighted in magenta, as you can already see, are almost never used. Like say water, we always call it water and not dihydrogen monoxide. It's so rarely used that even experienced chemists don't bother to say that. Now also, just like ionic compounds, we also use the prefixes like di, tri, and tetra. And you actually already have a video, but I made another chart just for refreshment. Also, this right here means that based on my experiences, these 5 prefixes, hexa, hepta, octa, nona, and deca, aren't too commonly used in nonmetals, as far as I know. So that was about bond energy, bond length, bond strength, and a little bit of nomenclature. Thanks for watching, and see you in our next AP Chemistry series. Bye!